So we're very happy to have Tina Kanstrup from University of Massachusetts Amherst, who will tell us about link homologies and Hilbert schemes via representation theory.
Okay, so thank you very much for the invitation. I'm certainly very happy to speak here. So this is a joint work in progress. With Roman Besrukavnikov. Okay, so the general goal is to unify a bunch of different approaches to Koranow-Rosansky triply graded link homology. So at the current stage, there will be no triply grading. I'll just try to first establish my result on the level of vector spaces, and then I'll try to deal with the gradings later. So goal, unifying different approaches to Koranow-Rosansky homology. So no worries, Matt, you're actually kind of half an hour early because I'll be starting from the beginning. So there'll be nothing in the first half an hour of any interest to you. So so you can log off and come back in half an hour. Maybe there'll be something that interests you. Okay, so triply. Graded link homology. Which I will abbreviate HHH. That's last time I'm gonna write it out in full letters. All right, so let's make sure we are all on the same page. So a link is just a connection of knots that may be linked together. And well, maybe as the title and my general personality suggests, this is pretty quickly going to turn into, there's gonna be no actual drawing of links beyond the next 30 seconds. Everything will turn into representation theory, which may be linked together. Okay, so the main old theorem of Markov translate this into an algebraic language, because if it was just about links and space, I'm not a topologist, I'm out of here. But it turns out that links can be is related closely to braid groups, which is something that I can understand, or at least I have a chance of understanding. So I'll have to take links up to isotopy. And this is equivalent to taking braids in. So this kind of braids with n strands, or any collection of n strands. So this is the braid group on n strands. And then we need to mod out by something, and this called Markup Moves. And I'll tell you what these are, but first I'll just tell you how this correspondence go. So let's say I have a braid, and going in this direction is easy, the other one is harder. So what I do, my braid, to create a link, I just close up the strands. So I just take the top strand and connect it to the bottom ones. And this gives me a link. All right, so the markup moves. So there's 2 of them. And they're like the most obvious thing. So if I have 2 braids, well, stacked on top of each other, then this is the same as stacking in the opposite order. Right? Because if I was to just close these up, I could just slide one braid to go on top of the other, and that would be the same. And similarly, if I take a braid and then I add an additional strand and then I cross it with the outermost one, I should put here, see, then this is the same as the original one. Because if I close up, this just gives me a loop and then I can just pull this tight. And the same way with the opposite direction of the crossing. All right, so what is triply graded homology? So it's something that takes a braid and produces for you a triply graded vector space, hence the name. And it goes via complexes of circle bimodules. And I'll tell you what, maybe I should say the homotopy category of complexes. Okay, so let me quickly tell you what circle bimodules are in tab A. And I don't know anything about, well, they exist in other types, but I don't really know much about them. So I'll restrict myself to type A, which is also the only type that has such a nice connection to links. I think you can say something about some of the other types, but since I'm not an expert on it, I think I will not go there. Okay, so let's just do tab A. So we fix some positive integer, and then we define R to just be the polynomial ring in n variables. And this, of course, has an SN action on it. But instead of just being the dumbest polynomial, I'll put a degree on these. And this is going to produce one of my gradings. All right, so if I just, let's take a simple transposition. So that's the one that switches I and I plus 1, say, then I can define my RS to just be anything that is fixed by this symbol permutation. So I just take any polynomial which is fixed when I interchange xi and xi plus 1. Okay, and so the thing I'm really interested in is this tensor product. And then I put a grading shift here. So this is maybe it doesn't looks so interesting at first, but it will be in a minute. Okay, so the category of circle bimodules is the smallest full subcategory of R bimodules, graded bimodules that contains R and this simple circle bimodule, and closed under the appropriate operations. So smallest full subcategory of R or graded bimodule containing R and all of my Vs for any simple reflection, and is closed under taking iron products, tensor products, grading shifts, and direct summons. And like the reason this category is interesting is a theorem by Circle saying that it categorifies the finite Hecke algebra. But we're going to use it. Well, this will be important later, but for now we're going to use it for a different purpose. So category. Finite Hecke algebra. Okay, so now let me introduce two complexes which will be the foundation of our link invariants. So we have two special complexes. So I'll name it the first one Fs. So it has my Bs in degree 0 and R shifted by 1 in degree 1. And the map, well, this is a bimodule map, so this just takes as determined by just taking the identity to identity. So this was what corresponds to a positive crossing. So this is going to be my dictionary between circle bimodules and what's like diagrams of links. And if I have one crossing, I should have something for the opposite crossing. And that something is the following. So now I put my R in degree -1, and then I took my Bs in degree 1. And this map is defined by setting 1 to xi tensor 1 minus 1 tensor xi plus 1. So this is a negative crossing. So this is the opposite one. All right, so from those, I can cook up a huge complex, which will be corresponding to a general braid. So choose a decomposition, because I can like any braids is like some sequence of positive and negative crossings. So I'll just pick some decomposition. Choose. Of so my my braid. So it would be like some sequence. So let's say, so epsilon stands for whether it will be positive or negative. So let's say I have k terms. So now I can construct this huge complex, which just take the tensor product of all of these two-term complexes. So something that is like in general not very nice to work with. And usually I refrain from trying to do calculations of this sort. I'll leave it to people who are better at circle bar modules than I am. Okay, so but the reason why like these complexes are nice is because they satisfy braid relations. And so like braid relations is like the first step towards a link invariant. So if you need braids, and then you need to have these two Markup moves satisfied. So definitely if you have something with braid relations and you have like some kind of chance of making a link invariant, really do something clever to it. So these satisfy braid relations. Okay, so how to cook up a link invariant from these. So for that, we use Hochschild homology. So let's just call the definition. So this is just I take the tensor product of taking x, I x in R bimodules of R with yi. And then I take my triple H to be something where I just take the two H's and take homology of those, complex. So if I start out with some complex, then what I do is I take homology of this complex where I take Hochschild homology of each of the terms. And then a final definition of my triply graded homology of braid is taking x, well, this is the ith derived factor of x. So you just like take hom and take the derived factor of this, and this is the ith term of this. So it's just like keeping track of this extra grading, because we want as many gradings as possible. Okay, and then I just take this big thing and apply this to this like complicated construction and apply it to my huge complex, and I get something which is not very easy to calculate. And this is where like geometry enters the picture. So what people want is they want to try to what some people want is trying to relate this to the geometry of Hilbert schemes. So let me state probably one of the maybe founding, at least to me, conjectures about Hilbert's relation between Hilbert schemes and triply graded homology. So this is Gorski, Negut, and Rasmussen. So the statement is that there exist two adjoint factors such that which can be used to calculate triply graded homology. Namely, there exists a pair of adjoint functors between the category of circle bimodules, where we need to start, and then something that is not quite the Hilbert scheme, but related to it. Actual Hilbert schemes will appear later in the talk, but for this conjecture, it will be this kind of weird thing, maybe weird looking thing. So I'll have two gradings, and then my space will be what's called the DG flag Hilbert scheme. I'll put, so this is kind of, this C2C is maybe like a not standard notation that doesn't appear in the paper, but it's just to distinguish it from C, because, well, it's not related to the Hilbert scheme of C, but it's something. So, okay, so I'll write up the condition, and then I'll tell you what this weird thing is. Okay, such that, so the first condition is that this is monoidal and fully faithful. Which is nice, but the most interesting part is that it can be used to compute triply graded homology. Otherwise, it wouldn't be in this talk. So calculating this is the same as taking my braids, or my, like, the corresponding Rukia complex, take the coherent sheaves, and then take cohomology of this sheaf. All right. So let me now tell you what this is. Okay, so first we're doing type A, so G is GLN, and B, my Borel, would just be all upper triangular matrices. And my capital, or like Gothic G, will be the Lie algebra. So it's just a set of all matrices. And my small b will be the subset of all upper triangular. And N will be the set of the strictly upper triangular ones, so zeros on the diagonal and whatever above it. So all of this is like type A. Okay, and yes, so the Hilbert scheme, so this is kind of like what people ideally want. It will appear later. From the Hilbert scheme, I'll tell you what is this weird flag Hilbert scheme. So the Hilbert scheme is, as I said, it's a set of triples. No, I think I'll want to write it in the G quotient form. So no, I want to write it like this. So I have two matrices, and then I have a vector. And my requirement is that these two matrices commute with each other. And then I require my vector to be cyclic, meaning that if I take and apply like any combination of my matrices to V in all possible ways, then these needs to generate all of Cn. And then I take quotient Ig. Okay, so what's the flag Hilbert scheme? So maybe I should note maybe the more standard way to think about Hilbert scheme is as ideals, and like this way. And the flag Hilbert scheme is a sequence of nested ideals. But for this point, like purpose, it's more convenient to write it in this way. Okay. So now I have 3 things. So I have, well, 2 matrices, but I want one of them to be nilpotent. This is this kind of weird like C part of the notation. If I like take the usual Hilbert scheme without the C, I would have put my just G here. So this is the nilpotent. And then my flag variety, G mod B. So, and well, in type A, this is this sequence of vector spaces. So each of them have dimension equal to its index. And so what I require is that my matrix Y should preserve the flag. So if I take my matrix and apply it to like one of these in the vector space, it should stay within that vector space. And then, of course, since it's Hilbert schemes, they should commute. And I still want to have my stability condition. I want to say the kind of reason why people might like flag Hilbert scheme is because like usually it's not like how do you go from one dimension down, because this is kind of like what people like to calculate with circle bimodule. They'll take a braid and then they'll try to like deal with one crossing and go one dimension down, and that's not very easy to do with a Hilbert scheme. But if you have a sequence of ideals, you can just like drop one of them and then you have your correct dimensions. So this is kind of their motivation, I think, for why you would want to have this flag version.
Hi, Tina, just a quick question. So can you think, you can maybe think of this flagged Hilbert scheme as some kind of bundle, or not bundle, but fibration over a Springer fiber or something?
Yes, so actually kind of like the point of my, like the very last thing is I'll give you a construction which kind of like gives you like will produce pretty much the space starting from the, so that's like the way I like to think about it. But I was like, so maybe I could save your question for the end of the talk,
Sure.
and then you can see whether you like that answer, and if not, feel free to repeat the question and I'll try to say
good.
something more satisfying.
Okay, thank you.
You're welcome. Okay, so so this is a very singular space, and the way people usually deal with very singular spaces of this form is they want to derive them. So maybe I should rewrite this in a different order, or in a different way. So I could look at this space, and then I could see, well, this condition is taking a fiber product. So where my map is just to take my two matrices, take the commutation, that's it, map to G, and I require this result to be 0. And well, this way of looking at it gives a nice way of like how you should think about it, because the problem is that this is very singular. And derived algebraic geometry tells you that to deal with this, you should replace your fiber product with a derived fiber product. So I should put an L here. So solution. Well, it's a solution if you like don't like singular phase, but it like you pay a different price. So I guess it's a question of who you are, which kind of suffering you prefer. I think I prefer derived suffering to like super singular suffering. And I think that's at least like that's the convention of the authors of this paper. That seems to be the preferred form of suffering. Okay, so let's very quickly, what's the derived fiber product? So this is taking us into the DG world. So if I'm just going to do the special case where I have a vector space. So S is some morphism from my space into my vector space. And then I can define this corresponding to my derived fiber product to just take, well, this would be as a tensor product. Well, tensor product I can take derived. I don't know what geometrically derived would mean, but I know very well algebraically what it would mean. So I just take, well, if I have a derived tensor product, what should I do? I should take a resolution. So this is now a GG algebra with differential. Given by df is equal to f of s, and then extended by the Leibniz rule. So my convention of what should coherent sheaves of this be, well, they should just be like coherent sheaves over this DG algebra, so like modules over this DG algebra. At least in the affine phase, that would just be modules over the DG algebra. All right, so this is what they want. So now there exists an actual construction, well, a similar construction due to Oblomkov and Osansky, which has an a priori different language, but one of the points in my talk will be that this is exactly the same, although they look different. Construction. So in this, like for purpose of general definition, G can be any algebraic group. Of course, for this, the intended application, I'll have G be either GLN or occasionally the Borel. X smooth, complex G scheme. And then we have some G invariant function. And so the definition of what is called matrix factorizations of G equivariant So this is the following set of data. So we have two vector bundles. So these two are the bundles on X, called G equivariant. And the D's are maps between them. So my D minus 1 go from M minus 1 to M0, and my D0 goes from M0 to M1. This is supposed also to be G equivariant. And the condition is that if I compose these in either order, this should be the same as taking W times the identity. So all I will end up doing is just multiply by the function W, which is called the potential. I think we should name for it. Okay, so then I will denote G equivariant matrix factorization as this, and this turns out to be a GG category, because if you try to look at what would be maps between this, you'll see that although you have potentials here, you need your maps to square to 0. So this is an honest DG category. And then I can take this kind of slightly weird, maybe form of derived category, which is the absolute derived category introduced by Posadzalski. Namely, well, if I have a DG category, I can take its homotopy category. Well, that doesn't look very strange. What is a little bit strange maybe is I need to mod out by what's called locally contractible. And this condition is that there exists an open cover in the smooth topology such that when you take your module and restrict it to each of these, you get 0. And maybe one thing to note is that, well, maybe two things to note. So in the case where X is finite, this quotient is not even necessary. So this just goes away, and then this is the most natural way to have a derived category. The second thing is that this is slightly different from the formulation in Oblomkov-Nosansky's story. In the case where G is not reductive, but it turns out that you can actually write that these two are actually completely related, and we have a way to write that up. But for now, I think I will skip talking about these issues.
Sorry, can I ask? I actually am not familiar with the notion of a locally contractible. Is this so special to matrix factorizations, or is this a notion that's special to defined in any DG category?
I've only seen it in the contents of matrix factorizations.
Okay, so if X is affine, then what does this condition mean? Or is it empty?
So it's empty in this.
Okay.
In that case.
Okay.
All right. So, but kind of the upshot of this is that that this is an alternative form of suffering to the DG one, because what you would see, maybe I won't actually write down this theorem due to time constraints, but it's a general concept that you can exchange this derivedness for introducing a potential. So this is just two different ways of dealing with the same same inconvenience. All right, so let me state the theorem of Oblom-Kovalevsky, and then I'll try to kind of cook up the things that appears here, like kind of starting from definitions. So, because Oblom-Kovalevsky's motivation, whenever I like ask Lev, I get a long string theory explanation that I don't understand. So I'd like to have a construction that kind of like makes more sense to me, in the sense that I'll like take something that I know, do something to it, and then I wanted to spit out the spaces that I want, rather than trying to like guess where they should appear. Okay, so I think I have a tendency to speak faster than I write. Should finish writing my theorems before I start applying them. Okay, so GLN. And then they construct this category, which at first didn't like ring any bells, but when you can translate it, it turned out to be a dear old friend in disguise. So the potential, this was supposed to be G. So I just take trace, if I take the adjoint action of G on X, and I'll multiply these matrices together. And the statement is that this is monoidal. But the more interesting statement is that this carries a break group action by convolution. Okay, so let me say, like, for, let's say we have a braid, so let me denote the corresponding one, which I'm not going to write down the definition, because it's kind of like they like define it explicitly in the 2x2 case, and then they use like induction functors to get more general ones. So it's kind of not very pretty to write up. And okay, and so from this, they define a function into a space of the actual Hilbert schemes, or periodic complexes of Hilbert schemes. So periodic corresponds to, like, this would be just be matrix factorizations with potential 0. And so let me just agree with their notation. Maybe I won't state where the, so this is called their churn functor. Okay, so this is one part of the statement, and the second statement is that they can construct a link invariant, and this link invariant agrees with triply graded homology. So this is like 2 papers, well, more than 2 papers, I guess, like one constructing the link homology, and another saying that this agrees with triply graded homology. So they take a hom in this case, and then they take this functor thing. So yeah, in the interest of time, I'm trying to write formulas in the like fastest possible way that looks well, kind of enlightenment. So this is what will be, so this is this will be the units, and this is kind of the, well, the trivial vector. With fiber. All right. So these are all, this is an explicit definition, and this is like an explicit computation showing that in fact their link invariant does agree with the triplet graded one. So what I would like to try to do now is like taking more like in a bottom-up approach. So I want to invent these kind of spaces starting from the definition. So like kind of going the opposite direction. So how to get something like this is from the definitions. So do I have 7 minutes left, or do I have 13 minutes left? Based like, do I have a full hour, or is it like 55 minutes?
You have a full hour, yeah.
Okay, awesome. So I can, when we start late, I can also finish late. Awesome. Because oftentimes it seems like this like go to the, this delays goes to the speaker's disadvantage. Okay, so I don't know a lot about circle bimodules, but I like geometry a whole lot more. And fortunately, there's this theorem by Webster and Williamson, which translates these circle bimodules in terms of like a geometry that is like more like native to me. Or more. So Webster. Okay, so the first part is I can take, so this is a simple circle bimodules. So this would be if you take a reflection, you write it as a product of simple reflections, you tensor these together, and then the biggest direct summand is this thing. And this is usually not particularly easy to calculate. But fortunately, it has a geometric interpretation in terms of IC sheaves. So B times B equivariant IC sheaves. BW. So that's already nice. What is even nicer is that you can do the Hochschild homology directly this way also. So I can take, so this will again be homology, but of almost the same IC sheaf. And then like last one is that indeed also the maps in the Rukier complexes matches what you would like think for the sheaves. I think there's like pretty much a unique map like possible. So it's maybe not a huge statement that these like kind of have to agree, but or pull back and push forward. All right, so maybe let me make a drawing. So what's the relation between these two? So where does these IC sheaves live? So I could think of this, my IC sheaves B times B equivariant IC sheaf as living on this double quotient. And so I could also take B and take the diagonal action. I think the usual way is just to write B, but I think maybe it's actually the diagonal action. So maybe I'll put a diagonal here just to not confuse people. So my B equidiagonal where IC sheaves lives here. And in fact, this one is just the pullback of this one. That wasn't particularly well placed. Okay. And so taking cohomology just corresponds to pushing forward to a point. So like this is like geometrically what we're doing. All right. So this is all like a talk about something that is like circle bimodules and IC sheaves. So this is kind of a story about the finite Hecke category. So maybe let's now take a route to the affine Hecke category. And this is where these kind of spaces are going to show up, like the ones that appears in Oblomkov-Antonski, and this is where our like Hilbert schemes are going to show up. So going from the finite Hecke category to the affine Hecke category. Okay, so we have in the finite corner, we have the D modules or perverse sheaves or whatever. So we have D modules and G mod B mod B. And over here we have the finite, so the affine Hecke category, which is in terms of coherent sheaves. So basically, if you want a story about coherent, your story to be about coherent sheaves, probably you want to like have something that's related to the affine Hecke category. So N tilde is, it's the cotangent bundle of the flag variety. And in terms of entries, so this is just, well, a nilpotent matrix and a flag where my matrix preserves the flag. So just the same conditions as we saw above, and this is gonna, this is part of the point. All right. So there are different ways to get from here to here, or maybe to be completely honest, I should put here, because I'll be using, like taking associate credits. So what I should write here is technically mixed hot modules, G mod B. So you should think about these are just D modules, which has a given good filtration and then some other properties, but the other properties you can kind of forget for this purpose. So for me, when I like, read mixed hot module in this context, I just think about D modules with a granted good filtration. And then like kind of the magic of the story is that in this case, this is equivalent to the Langland's dual version. And this is a part inside the affine Hecke category in the D modules formulation, and due to statement of Roman, this is equivalent to the corresponding affine version. So this is like the complicated way of going from here to here. Probably like if you're thinking about like talking about like fancy geometric representation theorists, probably they'll like take this route. So this is a monoidal category, and so this is this will be a monoidal functor, and this carries a braid group action. The braid group action is due to Bishop-Koenig and Risch.
Sorry, can you say what is, can you remind, what is MH? I think I missed that.
mixed touch. You can like miss that and just think D modules with a good filtration. That's how I usually read it. Just like, okay, I have 2 pieces of information I care about, and then like something else that I don't really care about. But then this complicated way as well. There's a like much less complicated route to do. Namely, I could take my associated graded. So maybe the like real statement behind this, that this what's called the Steinberg is also a cotangent space, and it's a cotangent space of exactly this thing. So this is why it like, makes sense to take the associated graded, and it's a conjecture by Lohmann that these 2 roots are the same. I think, well, it needs to like correct the weight, but that won't be a big issue here. But for the purpose of doing this, if I'm dealing with link invariant, well, I don't actually care that much about like any element here. I have like my favorite elements that correspond to my braids, and I care about those. And so this is this functor is this 2 realizations of the affine Hecke category? I think that's roughly the title, or at least most of the words I said is like in the title, but they might be in a different order.
Sorry, but isn't that like from D modules on the affine flag variety?
Yes, exactly.
Wait, where's the affine flag variety?
What? So this is,
oh, I see. So you take like
yes,
the constant loops or something?
yes,
Okay, sure.
yes. So this is just like, this is just, well, I guess I should put Wangland's duals.
Thanks.
All right. Shoot, I'm already out of time. Okay, so the statement is, so I'm like tying all of this together is that in fact these braid generators exactly corresponds to Rouquet complexes. This is literally what if you took a Rouquet complex and like ran through this procedure, what you will get up is exactly the braid generator corresponding here, only you will like flip what is S with SN. So you're like looking at your braid from the opposite side. So maybe kind of reach braid generators corresponds to Rouquet complexes. And second, what this Oblomkov and Osansky, maybe I'll just, since I'm already out of time, maybe I just copy. Not sure if that was actually faster than rewriting it, but. So this is indeed also equivalent to this. Stop it. Probably it would have been faster to just write. But there's an additional C star action here. And so their braid generators coincide. So like the braid generators in the Brest-Recavnik and Reach story correspond exactly to the one Alexa and Lev are cooking up independently. Match. And like maybe one of the like really nice things, if you wanted to like actually compute things, is this when you take braids, this actual braids, not just a single one. This would correspond to taking convolution products. And when you take convolution products here, you end up, it turns out, with a coherent sheaves. So instead of having like this like huge complex, which is a tensor product of a gazillion terms, you end up with a sheaf, which it's exactly like 1 degree. So this is like what you get here is like, at least to me, a ton nicer than if you were to do the actual Rukia complexes. Okay, shoot, I'm overcome, but let me tell you what happens to this construction if I like go to the associated graded world. So there's a procedure from this. Let me skip saying very much about it and just write the result. So the starting point will be the Steinberg. And now this will, correspondence up here translates to another correspondence, translate to 2 correspondences that you can put together to 1 correspondence. So here, this Steinberg means that these two have 2 matrices and they're supposed to commute. And I have the same condition here, and then I'll need to, so I should write all of these as G quotients, G quotient, G quotient, and then I need to push forward to the point. So going like this becomes going like this. So so if I was to, my original like construction on the level of D modules, that would now become doing the following. So maybe it's already 3 minutes every time, but I'll be done in a flash. So associated graded is what takes. So you should think about this as taking us from D modules. So our starting affine Higgs category. And then I need to tensor this vector bundle. Then I need to take the whole thing, push it forward, pull it back, and then take a homology. So this is what this calculation of triplet graded homology in the D module setting becomes in the affine setting. And the punchline is that this is pretty much flag help DG CNC, and this is pretty much help. And pretty much here means I'll need to replace my group by my Lie algebra, which is not a big issue. Alexa and Lev have to do a similar thing, and it worked for matrix factorizations, so I can't really imagine it would like be any headache here. And this one is the projective GIG quotient of this one. And this is just taking this corresponding stability conditions here. So one of the things that I like about it, except apart from like being nice and canonical, is that this is a story that works in any type. So what you can ask, what is the Hilbert scheme in any type supposed to be? Well, you say, well, it's this derived fiber product. And if you don't like derived stacks, you can just take the projected GIT quotient with the character being like the determinant minus the minus first. So this would give me like what would look like a very convincing candidate for doing this type of stuff in other types. But since I don't know actually anything about other types, I think I will refrain from saying more. So I think that was what I was planning to say, or a very fast version of it. And maybe, well, one last remark is that I very much expect Alexa and Lev's story to be exactly equivalent to this construction. There's a tiny bit of massaging I need to do that I haven't finished, but I couldn't really imagine they wouldn't agree. Okay, now I'll stop. I'm already 6 minutes over time, so sorry about that.
Okay, thank you very much. That was a very nice talk, Tina. Any questions?